Good morning, my name is Amy Briggs. I'm with the Great Lakes Observing System, and we're working to make the concept of bathymetry data density and its resolution more accessible to a wider range of people. Today I'm going to talk about how that intertwines with our process. You may be familiar with this graphic. It's widely used to represent Lake Bed 2030, which is a similar effort to Seabed 2030 for the Great Lakes of North America. The graphic that you're seeing was commissioned by laws to show where we do not have high density data, represented as varying sizes of hexagons, and how that relates to our understanding of depth in these layers. So at GLOS, as I said, we had a crowdsourced bathymetry that we stood up with a partner organization called Orange Forest Marine, and we currently have 25 plus vessels out mapping within the Great Lakes, plus many more that are coming online. For the purposes of this presentation, the majority of those vessels are within Lake Erie and Ontario, and they are collecting single beam data with their onboard navigational system. And we developed a pipeline that automatically harvests the data and puts it into our cloud without the end user needing to do anything, other than keep gas in their boat. So our next step is to provide feedback to our volunteers, and we're looking to clarify where they are collecting data, where they should collect data, and how to portray this information easily to humans without any special training. Humans like my mom, who even navigating a single web map can be challenging to find and interact. Therefore, we took the hex graphic that I already showed you, and we made it real. And at the moment, we're only doing this with our crowdsourced bathymetry type data. So, we call it the hex map, because we didn't know what to name it, and we're very original. So we're open to naming it. But what exactly are we looking at here? So these hexagons are 400 kilometers across, which represents a point spacing of 400 kilometers, or in other words, there is one point at least somewhere within each of these hexagons. And as you can see, they're all fluid, filled. Good news, we're done. Lake Erie in Ontario, done. Crowdsourced bathymetry to the rescue. Well, obviously we know that's not true, or we wouldn't be here. And if we zoom in, we see that indeed some of the hexagons do not have data. So these hexagons are 50 kilometers across, which we've been calling a hex resolution of 50 kilometers, and then that's shortened to hexolution of 50 kilometers. And if we zoom in even further to the coast of Toronto, and a hexolution of 400 meters, bigger gaps are revealed. You can even start to see some of the vessel track lines. And if we zoom in even further to a hexolution of 8 meters, not only can we see individual track lines, we can start to see individual points. You may even be able to tell how fast the vessels are moving based on the number of gaps between hexes. So pictures are all well and good, but how does it work? How do we make data density accessible to someone like my mom? Well, all she would need to do is navigate the map and explore. As you can see, new hexolution or point spacing is as you zoom in, revealing different scales of gaps and points. And since we're collecting this data in real time, with the data processing pipeline that GLOS developed, we have the potential to see these results show up on their map shortly after collecting it, which is near instant gratification. And each filled out hex is its own reward. You could even say we're virtually handing out participation trophies. So, how does it work? Well, our volunteers are out collecting data that gets automatically harvested and sent to the GLOS file. Once it's there, it gets converted to XYZ data, and we send a copy to the DCDB as a trusted node. Then, it gets binned into H3GO. And H3GO is an open source hexagonal grid-based API that essentially bins data into varying sizes of hexagons, or in our case, hexolutions. It's similar to Google Maps. As you zoom in and out, different hexolutions appear and disappear. Once that's done, it gets displayed in Sli.do, which at the moment is just a prototype. So we're still in the beginning stages of this project. You can see a potential for a number of different applications. And where are we thinking we're going to go from here? Well, we'd like to put it into Sli.do and expose it to the public and our volunteers. We'd like to continue to recruit more volunteers for our crowdsourced bathymetry. We'd like to use it to educate the public on what data density means. We'd like to use it as a visualization tool with politicians and funders to demonstrate need. and we'd like to use it to advance the goals of Lake 2030. Thank you. If you're interested in hearing more or participating in any way, you can contact us at underwater@gloss.org or myself at linden@gloss.org. Thank you very much.
Thank you in absentia. That was great. And Linden works closely with me at Great Lakes Improving System, so if you have any questions about tax solution, this is a great word to go to next. And, or the project that we're working on with Sli.do, or the hex map that we've been building, so I don't know. Or like 2030 for that matter. Next up is Nicole Trenholm. Where's Nicole? There she is, from Ocean Research Project. She's the Science and Expedition Leader, and I will let you talk about your project. Okay. It's fascinating.
All right, thank you, Tim. Thank you, Matt the Gaps and Sli.do 2030. I'm really proud to be here. I'm really excited to talk about Go Marine, glacier oceans, mapping, and research interdisciplinary efforts. So I'm a co-director of a nonprofit organization, Ocean Research Project. And we sail for science, education, and exploration, and have conducted various campaigns to the Arctic up to this point. And so we've kicked off Go Marine this year with a slightly larger vessel, a little bit more capable. And I'm really grateful for our supporters, various public donations, private nominations, academia, and some clubs like the Royal Society, Explorers Club, Society of Geographers, and such. Okay, so why go north? What's this all about?
Every year, the Arctic's ice-covered oceans shrink, revealing uncharted navigable waters. These waterways, once frozen year-round, now beckon a new age of exploration. Each summer, Ocean Research Project sails north, observing and mapping the marine environment before extreme temperatures further devastate the polar region. There's a poetry to ocean mapping. The sailors swiftly navigate the polar waters in a complex dance, avoiding collision with nature's obstacles. Towering icebergs, hidden rocks, fog, wind, and waves all accompany the boat on an exhilarating performance across the coastal Arctic. Armed with the best in mapping technology, oceanographers tune the multi-beam sonar like a master musician, sending millions of sound waves from fingertip to seafloor. While those sound waves bounce off the ocean's bottom, satellites pass overhead, remotely guiding the ship's course and perfecting each depth sounding position. As the new ocean map begins to emerge, ancient markings and features tell of colder times during the last glacial maximum. By expanding coverage of the Arctic seafloor, climate models can better predict the pace of sea level rise and impacts from the warming of our planet. With over half of our planet's oceans uncharted and Earth's polar ice cap rapidly receding, mapping at the edges of the Earth is more important now than ever. The good news? We're up to the challenge.
So I hope you have a sense of the motivation and the spirit that we have for participating in this global effort, and continue to plan ahead to do so even further. So Ocean Research Project kicked off in 2012, and we've been going up to the Arctic several different times for hydrographic campaigns, contributing to the Ocean Melting Greenland campaign, a mission of NASA, and some of the work that they've done in Northwest Greenland and such. So we keep going up there now, and we're broadening our plans for our surveying activity. We have an overarching question that we're interested in exploring, and that's how does coastal marine ecosystem respond to deglaciation across the Arctic? And we need all kinds of observations to be able to truly investigate, these changes and the causes and effects of these changes. So we need acoustic, optical observations in situ, right there, from some kind of vehicle of sorts. We need water samples to validate those optical and acoustic observations. We also need remote sensing satellite imagery as well to truly get the pulse on the change of the coastal glaciated areas. a little repeat about the mission objectives for Go Marine. So we want to eliminate these geophysical unknowns, these gaps in these glacial fjords. These fjords and coastal areas amongst the glaciers, the Arctic, you need that information to better improve the climate models, some of the base information that gets plugged into these climate models. So therefore, we contribute 1/3 of our time, our operational time when we're up in these regions towards dedicated mapping teams, towards multi-beam data collection, to go to these important topographic and bathymetric grids. We also characterize the coastal ecosystem underway and the water quality, utilizing those optical and acoustic measurements as the deglaciating landscape evolves and changes. And we also use that information near real time to make decisions about exploring the geomorphologic features of these coastal fjords. So we can reconstruct the history of the coastal glacial mobility over time since the last version maximum. And we can also explore the ecological conditions from that period by near real time collecting seabed cores after reviewing some of that fresh bathymetric data. And so, as I said, some of our outcomes is contributing this acoustic bathymetric data to JEPCO IDCAL grid, bed machine, which is a topo bathymetric grid, just kind of based about the Greenland ice sheet, various scales. ADAMAP is another regional model that's coming together in the Canadian Arctic that will be contributing more data to. And then also this information ends up being plugged in to help with estimates of freshwater runoff volume, rate estimates, sea level rise rates, geohazard susceptibility hazard locations around communities that are near these glacial fjords that have unstable coastal underwater structures where landslides can cause major tsunami events, or areas where there's potential for large flood outburst zones. So the more of that subterranean coastal geophysical information that we can plug in and sync up with the topographic terrain, the digital elevation model, the better it is to make some projections and estimates of what we intend to assess going forward. We also use the satellite ground truth observations to start to explore how water quality is changing across these different glaciated coastlines. So what you see from space is giant sediment plumes coming off the Greenland ice sheet. You see algal blooms that are popping up throughout the season. So how can we interpret that satellite information? We need to collect these observations in various approaches. We can also go ahead and explore the role of the coastal Arctic relative to carbon burial, carbon sequestration. And we can do that by interpreting the geomorphology of the debris that we're collecting and collecting some samples, of course, and such. And so thank you, Marie Tharp. So we named the vessel after her, commissioned her, and christened her back in May. It was a very exciting time for the Ocean Research Project Group. And so, of course, Marie pulled all those fathograms together in the 1950s and made this beautiful chart of the world seafloor. And in doing so, she helped with the theory of continental drift, exploring and finding these rift valleys. And so we wanted to honor her by naming our expedition vessel after her, and even our campaign name over the ocean decking, Go Marine, after the amazing contribution that she has provided and the inspiration that she is. And so we are also, yes, cost effective, but we're also generating very little fossil fuel emissions. Over an entire season, we generate what a traditional vessel working in these areas would contribute in 1 year. So that is a nice thing that we can do as part of our mission in mapping these regions. We are starting to develop our global team. Many advisors relative to the strategy of the polar coastal mapping areas, priorities. We also have advisory relative to the hydrographic operations and technology. We have a number of researchers that we're working with that are experts in acousticians and geochemistry, sedimentology, optics, and so a great group is coming together and really wanting to make the most of these data sets and start to plug them into the right models so that we can really start doing as much as we can with these data sets. And so that includes some familiar faces, Larry Baer and Martin Jacobson have been involved in helping review and consider the different priority areas of our glaciated fjord surveys. Same thing with some of the folks who are associated with the NASA Ocean Melting Greenland campaign, who developed these models and informed us of some of the missing areas that during their mission they weren't able to get to. And some of this information is still very important because they remain undiagnosed relative to helping have a better Greenland ice sheet melt estimate and model. So there's 87 glacial fjords remaining in Greenland ice sheet alone, and we're going to tackle as many that we can safely and have fun while we're doing it. So why did we go to Southwest Greenland first this summer for a couple months, coming up from Maryland, taking a couple weeks up and a couple weeks down, Dodgers and Hurricanes, and we're like, well, it was the maiden voyage of this vessel, so we didn't want to overcomplicate things by going too far and going up into the above the Arctic Circle and into some areas where you really have to pay attention to pack ice and manage that. However, this is an important area because this is an area of some of the most glacial meltwater runoff. It's a hotspot for sediment runoff, and you see this kind of colossal biomass production, this algal bloom, you see this every season, waves of it. So there's a lot of physical oceanography that's interacting with the coastline, and we did not have much understanding. There's very little information about these glacial fjords and the hydrography of them that's influencing this important productive area where we know we have important fisheries operating in these regions. And southern Greenland is an area that is, you're seeing more and more tourism, boat traffic, and the like. Oops. All right, so that brings me to MACA-GAPS, which is our fabulous partner that we brought on to be able to be ready to conduct this project and kick things off for the Ocean Decade. And so MACA-GAPS brought their expertise. They helped with the mobilization of our sponsored R2Sonic 2026 sonar that we integrated onto a universal sonar mount mega tower, bow mount, and so they are kind of bringing in that talent and participation of the JEPCO alum, and we intend to keep doing that. We're also going to be working with them also on kind of side novel research and publications that have come from some of the kind of extras that we were able to conduct. Multispectral frequency backscatter, R&D studies, looking at water column, and taking a look at some of that interesting geomorphology. So we ended up mapping an area that's almost 8 times the size of Southampton. And so we reached nearly a dozen fjords that influenced by different stages of glaciers, all surrounded by the major town of Pavia, which used to be a major fishing town for cod and such, but then the cod fishery crashed. So anyway, this town is kind of was our little hub, and we worked in this area for 1 month and collected an incredible amount of data. So this is a little bit of what the seafloor looks like. There's some of these ocean terminating glaciers, retreated glaciers. You see all kinds of interesting features demonstrating pathways of some of the meltwater, the pre-existing position of the glaciers hanging out on a ledge. So this information was so great to have in real time to collect all the water column samples, the seafloor sediment samples for when we return after the primary survey. And many deglaciated fjords as well showed signs of glacier advance in the past. These interesting little sills, maybe not so little actually, And so I'm going to keep investigating, utilize the QPS software, another sponsor doing meshes and investigating what these features are, what they may mean to tell us. And so we conducted we're doing glacial geomorphology. We have some academic experts helping us with that. Same thing with sedimentology. We also use ADCP to look at the backscatter water column of that, so we can compare with our multi-beam sonar data and optics data. And we'll be looking at those ground truth to figure out what the geochemistry is, what is the ratio and concentrations of organic and inorganic, how much carbon is truly being buried in these regions. All important questions for the carbon budget to know more about the changes in the Arctic. And then relaying that to what, interpreting those developing up and coming that are, okay, that's pretty much close to being done. But yeah, we got those satellite ocean color models. They're developing higher spectral resolution. We need to interpret them. We can keep forecasting in the future. If we understand water quality, the glacier coastline of the Arctic. So looking ahead, data submission is coming to IPCAL and CBED 2030 relative to this project, a little fine tuning with some processing. We're going to do a couple modifications to the hull and some onboard technology for Marie Tharp. So we're going to be going back up to Northwest Greenland and the Canadian Arctic next year and continuing our surveying activities and our oceanographic research with our academic partners. So thank you. We couldn't do this without our industry partners. We cannot do it with all these experts. And just to note that we need everybody, big boats, small boats, sailboats, citizen science, autonomous, satellite-based derived with imagery. We need everybody. We're going to map out this blue ball. Thank you very much.
Thank you, Nicole. Don't go too far. Do we have any questions for Nicole? We do have a few minutes.
So, I think I saw somewhere written are you working with the Canadian Hydrographic Office Service?
So we will be, because we're going back up to the Canadian Arctic next year.
Because they're very active there, and also the Geological Survey of Canada from the Bedford Institute. Mm-hmm. So if you're interested, I'm happy to get you in contact if you are not already, because they're really active. They got massive funding from the Ocean Action Plan to go up.
Yeah, I appreciate any connections, and mostly it's been some of the researchers at University of Alberta have been doing a lot of mapping work in that area, and then and just interacting with the Nunavut Impact Review Board previously. So yeah, any connections, appreciate it.
Yeah. Want to go in the boat?
Yeah. Wow.
All right, thank you very much, Nicole.
Very much.
Next up, I didn't see any questions on Sli.do. I was monitoring. If we get any in, I'll make sure I forward them to you. Ash Skett, Director of Operations from CTIP International. We talked about
Cool, thank you very much. Sorry, I don't have that. You have the presentation? So I do admire everyone who can do these presentations without their little notes, but no, I'm not that good at that good at memory. But no, nice to be here, and thank you for the opportunity to present and give this talk. My name is Ashley Skett. I'm Operations Director at CTIP International. I've been lucky enough to be working with the company for 4.5 years since we launched our first vessel, USV Max Lima. And then since then we've done quite a few groundbreaking projects, you could say, as we've gone out to the Atlantic on surveys across busy shipping lanes with our USV. And I just find it so exciting and challenging and rewarding to be at the forefront of this technology. you could call it the biggest advance since the invention of the combustion engine. So it's a really exciting time for the industry. I'm here today though to talk about our project in Tonga. Now I know we had Kevin's got brilliant presentations yesterday, so I apologise in advance. A few of these slides will be a little bit of repetition, so I'll just kind of just breeze through them. We should have probably synced up, but never mind. Yeah, we're going to talk about Tonga and what we did this summer, and then hopefully show you a little bit about what USBs can offer going forward. In January, Tonga Hapai volcano erupted, sending out a sonic boom that was felt, as Kevin told us yesterday, all around the world, travelled around the world. It caused a lot of damage and 30 millimetres of ash layer on the main island. Submarine cable breaks. It was a live eruption, as Kevin said, since Krakatoa in 1883. I think that image there shows the violence of that eruption. Again, sorry to repeat, but I'll breeze through it. There were two islands connected by the caldera, and that connection disappeared on the eruption immediately afterwards. And you can see in those comparison photos, the before and after, the kind of impact that it had on that island, and the amount of ash you can see from there. You can imagine like the respiratory problems that something like that would cause. So, in order to understand what actually happened and how this could happen without warning, and how could we potentially predict these in the future, the Tonga Eruption Seabed Mapping Project was formed and funded by the Nippon Foundation. We've obviously got a bit of history with the Nippon Foundation, as they funded the development and the build of Maxima, this vessel that we use for this project. So it's really great to be working with the Nippon Foundation again. The Nippon Foundation contracted NIWA to do the work, and NIWA did, as Kevin said, the outside the caldera, and we focused on the centre, the crater. The reason for that is quite obvious. It's quite a significant safety hazard, a still erupting volcano. And there's a great slide that Kevin showed us yesterday in the dangers for a manned vessel to be operating in that kind of area. There's a natural fit for our USB. USB operations are considered less dangerous because there's no people there on board, and they have the added advantage of minimal fuel consumption when compared to manned vessels, which is obviously better for the environment. The logistical challenges were quite significant. So we're talking 15,500 kilometres from our base here in Salisbury, all the way to Tonga, operating a vessel on the other side of the world. Our operations centre was in the UK. The vessel was initially mobilised in Nuku'alofa and then deployed over the volcano. So you can imagine the other kind of challenges we faced with the infrastructure having been hit by that eruption, and getting those, I guess, getting the equipment ready and being able to deploy a vessel and lining everything up in such a remote location, which was in the midst of a lockdown with COVID, and we had to deploy a team of 3 guys out there to do that work, and a huge amount of hurdles to get that team out there. But we were helped along with the British High Commission, which we were very grateful for. But yeah, when this project was first initiated, it was a full lockdown on top of it, and no in and out. So thankfully, things had eased off slightly by the time we actually came to do the project. And then there were other challenges. We had to get permission from the flag state, which I know probably some people in this group have experienced. It's not an enjoyable process by any stretch of the imagination. That took us about 3 months to get permission to undertake this project under the UK flag. And it's a lot of work, and it's quite slow sometimes, the wheels turning, but we got there in the end, and fortunately, just in time, we were able to do the project. So we mobilised our vessel first thing in Ipswich. This is in the UK. It was in a refit at the time, so we launched it. We did some testing, and we modified the vessel slightly. We installed a winch at the back, all of this was done in the space of 2 weeks. There's a time pressure on it. If we wanted to get it out there for the summer, within the timescales, we had to get it on the ship. And as it turns out, the ship was delayed, and it took 3 months for us to actually reach Hull in the end.